Hello all, this is Gator. I am showcasing the 3D Navmesh project I have been working on. So if we hold Q here just to visualize, these green boxes are not actually the objects. They, all of the information is stored in an array, and then when Q is pressed, it is just visualized with these green boxes and the red arrows. Um, so you can see that each box actually knows what its neighbors are. Um, Even going up a slope like this, it is able to tell what boxes are reachable. And then on the edges, like here, it knows that it can't get up to there. It is separated. Um, and even more than that, it registers Z difference. So these boxes know that they are not connected to the boxes up here. The boxes up here have their own separate island of Navmesh boxes. So there's a couple of different things it filters by. First, it filters if it's even within 150 pixels. Then it filters if it has a line of sight on the object with a raycast, and it also filters if the object is less than, if there's a difference on the z value of less than 15 pixels. Um, and it also filters to make sure that it's not including itself in the list of objects it's connected to. And all of this information, the coordinate points and the connected objects are stored in a structure variable. Um, so what is happening here is that from this positioning seed object, it is raycasting out, and it is adjustable. Um, right now I have it set to 64 pixels, and then it iterates 30 times on the X and Y uh, axis, um, which is more than enough for this little scene here. Uh, and then also, if it does detect a valid raycast, it moves down an adjustable amount and then it raycasts again to make sure that there's nothing underneath that. It tests for overlap. Um, and that is adjustable too to make sure that you don't have a situation where there's objects in the wall. If there's collision that is slightly overlapping, like here, um, and like that. See, normally you don't want that to happen, but that's slightly more than the offset, so it goes through. But because the raycast, these are actually part of the island. Um, so if an object was here, it wouldn't be able to get there, even though they are connected here, because the raycast coming out of an object won't pass. So um, that's a bit complex to explain. Anyway, I'm just really happy with how this is turning out. I think this looks really cool. um, but yeah, these are 15 pixels, so it knows it can get up this if you're using. Uh, Assumedly, you would be using physics object as the character controller for whatever you are doing the Navmesh with. Um, but this project is available for free on my itch.io page, which is linked in the description. It's not exactly a drag and drop solution, and it does have some caveats I will go over. Um, but everything here is annotated to the best of my ability, and then I will be explaining everything in this video. But first, just to go over the caveats, uh, this is not something that is easily editable. Um, so this is stored in a global variable, right? Which means that after runtime, the information is lost unless you do something where you save it. There are a couple of different ways you can save information in Gdevelop currently. I have this export set up. That's ooh, ignore that. Um, I have it saving into a JSON file here, and theoretically I could load that JSON file, and I wouldn't have to recalculate the Navmesh. Except if you are doing a web export, you cannot use JSON files. It won't let you access that file structure. Um, so really, it's the web directory that is. If you were doing a web export, it is difficult to save and load information that you have created during runtime. So this is not something that you would be able to edit in this editor, because it is actually generating it with the 3D raycasts. Uh, so you would anytime you would make a change to the map or anything, you would need to go through and then run the nav mesh generator again. But once you actually have that nav mesh, you can use it. Theoretically, if you were doing this on a local device, you could save it on the local device so that a player would only need to run the nav mesh generator once. Or you could even, if you weren't planning on doing a web build, you could just package that JSON file into the actual export. But getting into actually how this works now, there are three distinct steps. So we start with the nav mesh generation, then we compile the nav mesh points into cells. And cells are basically volumes of 3D space that we are defining. Uh, and then we are using those cells to determine, because if we just checked the validity of every point on the scene, we're going to be checking hundreds of objects potentially in a single frame, or uh, a few sequential frames. And that's going to be very taxing. But because we compile them into cells, it can just check the neighbors of that cell and objects in its own cell instead of every node on the scene. So starting with this raycast detector, what we are doing is, while this raycast build variable is true, it is going through once every frame. And I did try to do this with repeat variables, so it would be happening more than once a frame. But I was running into trouble using this raycast 3D extension more than one times a frame. Like, it will work theoretically if we have it in multiple events like this, but for whatever reason, if you do a repeat, one of these objects, one of these actions, and you say repeat it 3 times, what I was discovering is that there was some glitch happening where, regardless of whether or not the raycast would be valid, it would pass as valid as long as a wall object was on the scene, and it would return 0, 0, 0 as the 3 coordinate points. So we just had to slow it down a little bit. So this whole event runs once every frame. It's a loop in that sense. So when it casts, it saves the X, Y, and Z intersection, and it rounds them down to a decimal point. It saves them in a navmesh variable. Then it saves the Z intersection minus that Z offset to the raycast dot Z loop, and then it says it increments this raycast dot hit, which is essentially the ID value. So as you can see in this nav mesh, it assigns it to navmesh dot raycast hit, which means that the first time, since it is set to 0, the first time it will be assigned to navmesh 0x. The second time the raycast is valid, it will go to navmesh 1x. The third time it will go to navmesh 2x, and so on. And then it is saying that it did have a valid raycast. It is setting raycast valid to true. And why that is important is that is how it knows that instead of moving the raycast along the X or Y axis, it is instead moving the raycast down. to cast again to make sure that there's no geometry underneath the surface it just hit. And that is how in this scene, it knows that it hit up there and it needs to hit again, and it hit down here. And a nice thing about this raycast extension is that it doesn't hit on the inside of the box objects here. So if you are raycasting just underneath the geometry, it won't actually trigger, which is again is really nice. That's how it knows to raycast again in that same spot, but slightly down. And it will do that until it no longer detects raycast, until that raycast passes as false, which will mean that we add one to the while loop, which will move us along the offset here in the y-axis, and then it will set the z loop variable back to that raycast seed object origin. The raycast seed object is that red box here, and that is where the raycasts start at. So you could theoretically position this anywhere on the scene, just as sort of you don't always want it to start at 0, 0, right? Then it does that until both y loop and x loop, which any of these raycast variables are actually scene variables, which is why I hesitate to call it a drag and drop solution, because you will have to make sure you have this raycast variable here and this superstructure, but we'll get to that. But once you have filled out the y loop and the x loop, it sets raycast build to false, and that is how it knows to move on to cell compilation. And cell compilation, if you remember me saying, essentially a cell is a volume of 3D space. And any point it detects in that space is added to that cell. And the reason, again, this is important is because if we have these cells, when we go to check neighbors, we don't need to check every node on the scene. We only need to check nodes that are in that cell and nodes that are in cells adjacent to that cell. And so the way it knows what cell it is in is this clever little trick here. We divide the x, y, and z of that node, and we put those, and we floor it. We floor it. We divide it by the grid size, which is 128. I had better luck with different results. I found that 128 works, something that is twice your offset. Just something that has a good volume of space in it that can encompass a number of nodes. And we are setting these cell X, cell Y, and cell Z variables. So we take those and we go into here. We're doing this for each child in Navmesh, right? Each child in Navmesh is one of those coordinate points that contains the X, Y, Z, and neighbors, right? The neighbor IDs. So we are going through. Then here's this cell superstructure I was talking about. And the cell superstructure is like the Navmesh superstructure, right? But instead of containing the coordinate points, each cell has that X, Y, and Z key and a list of nodes in that cell. So what we are doing here is we are checking to see if the cell key we generate with the Navmesh is valid for any existing cell. And if it is, we pass the ID of that cell to the target index. And if it is not, we generate a new cell with that key. Then, regardless of whether or not we found a valid key, we add the iterate variable to that target index dot points. And that is how each cell knows what node is in it. Once this is done, we activate the neighbor check, and we move on to check in the neighbors. This is not mathematically complex. It is just slightly logistically complex. So basically what we're doing here is we are generating that cell key from the Navmesh point again. And we are getting all of the nodes in each adjacent cell. And we are doing this by essentially taking the key and adjusting it by +1 or -1. And so we grab all of the point children, and these points are just the array reference number to the object that is in Navmesh. So each Navmesh, it is sort of laid out like it's sort of laid out like that, right? We have the Navmesh, we have the point, and that point is the ID variable, and that ID variable is what is referenced here when we append all elements from the array into Navmesh. So now that we have this valid Navmesh list, which is a list of IDs, just numbers that represent objects in the Navmesh array, we need to filter this Navmesh list to make sure that the points have a valid connection. So the way we do this, there are currently 4 checks we make here. We need to make sure that the nav meshes are not the same point, because the list of all points in a cell will include the point we are checking, right? We are checking the distance between those 2 points with 150 pixels. And that can be increased and decreased depending on how many neighbors you want the nav mesh to have. We need to make sure that each point is within 15 pixels on the z-axis. And this is important for physics-based character traversal. And this 15 pixel difference can be adjusted based on what you need for your project. But this is to make sure that a ramp is not too steep, or that a slope or a ledge cannot be traversed, 15 pixels, I think, is a good starting value, but play around with it, And then finally, we need to make sure that the check, that it is actually a traversable thing, and we do that by calculating we cast ray against the wall there. And then if all of those conditions are true, we add the value to the connections in the nav mesh. So this final event group I have here is just for visualization. So as you can see, we have these raycast test objects, and for each nav mesh object, I keep saying object because it's not like a physical object you can drag and drop on the scene. It's a data structure that I'm calling an object because it has, it represents a thing. I'm sorry if that's a bit confusing. But it is creating this raycast object at the position that is stored in that coordinate point. And it is also giving the ID of that coordinate point. Then, if we are looking at a raycast test object, it is going to create these Navmesh tracker objects, and it is going to show which connections that Navmesh has. And so that's it. Once you have done, once you have run that program, you then have an array that contains structures that have a coordinate point and a list of connected coordinate points. And from there, you can run a pathfinding algorithm like A star. I like A star. A star is pretty good. It's um, yeah. But once you run that, you'll essentially need to give your enemy objects or whatever you're using on that pathfinding. Uh, you're going to be giving it coordinate points, and you're going to be telling it to navigate to each coordinate point, and then when it reaches there, strike that coordinate point off the list and move on to the next coordinate point. And that's basically how you're going to integrate it. It's not as clean a solution as the 2D nav mesh options. Um, Unfortunately, this isn't, as I said, this isn't a drag and drop solution. You at least need a few objects on your scene. You at least need a few different extensions. Um, and it does take a little bit of finagling. But it does generate a nav mesh. So I guess what else more do you want, right?